All right, everybody, welcome back to CS 125 Online. I am really happy to be with you guys today. I hope everybody's well. I hope you did great work on today's midterm. The scores look excellent to me for those of you that took it this morning. So today we're going to move on. We're going to finish up talking a little bit about lists. We will then move on to the next data structure that we're going to talk about this semester. And this is a data structure known as a tree. Trees are an extremely common and powerful data structure in computer science, again, because they allow us to implement certain new types of algorithms on top of them. And this is not the last time you're going to hear about trees. You're going to hear about trees in 125. You're going to hear about trees in 173, 225, 374. There are many different types of trees that you will eventually become familiar with that are suitable for different types of algorithms. One of the reasons that we talk about trees in this class is to introduce this idea of recursion, which is a new programming technique that is going to allow us to solve problems in a way that turns out to end up producing extremely elegant and concise solutions. So far this semester, we've looked at one particular way of implementing algorithms to solve problems using an iterative approach. And in recursion, what we do is we take a different approach to solving a problem, an approach that looks at ways that we can make the problem smaller until we identify very, very small subproblems, and then find ways to combine the solutions from those small problems together to end up solving a larger problem. Okay, but the place where we're going to start today is reviewing our linked lists. You guys have a homework problem to finish today about this that we opened up on Monday, and then you'll have another one tomorrow to wrap up our implementation of the linked list, the simple list interface, using linkage rather than an underlying array. So let's go back and review our insertion algorithm. This is one of the trickier parts of getting linked lists right, is figuring out how to do inserts. And once you can do an insert, you can kind of pretty much do a remove as well, okay? All right, so here's our algorithm. So essentially we want to put something into the list. We know that we have a list where the internal structure consists of items that are linked together. And in order to insert an item, we essentially have to adjust some linkage in the list. So when we insert it into our array, we have to move all these items around. That turned out to be very expensive. For a linked list, insertion should be pretty easy once we get to the right spot. Essentially, we need to do two things. If you think about, I've got like a chain of items that are pointing at each other. I need to stick a new item in there, which means that the preceding item, its next reference has to change. And then the item that I'm inserting has to have its next reference set properly to refer to the rest of the list. Okay, so here's my algorithm. And again, we have some diagrams to go through this together because summarized in English, it's not necessarily all that useful. So first we're going to find the right spot. Then we're going to set the next reference on the preceding item to point to this new item that we're inserting. So we have an item that I want to insert. In order to insert it in the list, I need to find the previous item and modify its next reference. So imagine again, I have this list that I've created of all the students in the class where I've each given one of you the name of another student. That's the next student in the list. If I want to stick somebody in there, I need to find the right spot, and then I need to go to the person before that person I'm inserting and say, okay, well, your next student used to be, Susanna, but now it's going to be Lily, right? And then Lily, the student that I'm inserting, whoever Susanna's next student was before, I need to say, okay, Lily, well, your next student is this person. And now I've adjusted the right linkage, and I've inserted this new student into the list, okay? So I need to change the next reference on the preceding item. And then I need to set the new item, I set its next reference to point to the item that used to be next, right? Okay, so again, let's go through slowly, carefully, an example. An example showing our diagram, right? So if you have questions today, I have turned off the live stream mainly because there's just a lot of sort of random chatter in there, and it wasn't really a good venue for ask questions. The place to ask questions is right here, and I'm sure Elon Tusk will have some Fantastic questions for us today. There are, happy April Fool's Day. There are some little mini-me's running around the forum. Don't worry, I've got my eye on them, and I'll make sure that whatever they say seems to be something that I approve of. I kind of wish that they would, hopefully these little mini-me's will stick around for a little while and kind of keep helping out, because so far the things they say I'm in complete agreement with, so that seems to be working out very well, for me at least. All right, so let's go back and go back to our, get back there, our list example. Okay, so here's my list. My list currently has 3 items in it. The linked list itself holds a reference to the start of the list. That's an item with value 5. That item holds a next reference to the next item in the list, which is an item with value 8. And then that item holds a next reference to the last value in the list, which is item 1. That item, its next reference is null. That indicates that it's the end. There are no further items past that point. So what I want is, when I finish, I want this list to have 4 items, and I want this new item I'm creating with value 7 to be at index 1. Now note that this means that item 8, which was normally at index 1, needs to move down to index 2, and item 1, which is normally at index 2, needs to move down to index 3. Okay? So here's what I need to do. So this is where I want the item to go. But if I want the item to go here, if you'll look, the arrow that I need to adjust is actually the next reference from the preceding item. So the first thing I need to do is actually walk to the spot before the place in the list where I want to insert the item. So if you want to insert it at index 1, you need to walk the list to get to index 0. If you wanted to insert it at index 5, you need to walk the list to get to index 4. In general, if you want to insert it index n, you need to walk the list to the index n-1. And this makes sense. So think about if I'm inserting at the start of the list. So the start is index 0. What does it mean to walk to index -1? It means to change the start reference itself. And that's what we did in our add to front implementation. We just modified start directly. So here I'm going to walk the list to get to the item 5, which is currently in index 0. And now I have access to its next reference. So now I can do the first thing I need to do, which is to get item 7 into index 1. Okay, so what I do is I change the next reference on item 5 from referring to item 8 to referring to item 7. Okay, so that's first step. Now I'm halfway done, in the sense that now item 7 is at index 1, but the problem is I've detached the rest of the list, and so I need to reattach that. The way I do that is I set the next reference on item 7 to refer to item 8. And that's it. That's all I have to do. And you guys will have a chance to do this on the homework problem if you haven't already. And again, this is one of those sort of canonical problems that you end up having to be able to solve in other contexts frequently, right? You guys will get on to 241. You'll have to do this type of thing when you're working with linked lists in C. And if you can do it in Java, you have a reasonable starting point and be able to do it in other languages that aren't quite as forgiving. So, with that under our belts, just to do that as a bit of review, what I want to point out before we move on to trees, I just want to have a couple of other things I want to say about lists. So the first thing is, right now, the type of list, there are many different types of lists, actually, and the type of list that we've been talking about is something that's known as a singly linked list. What does that mean? It means that each item in the list has one link, and that link leads to the next item in the list. So what this means is that each item only knows the next item in a particular direction, right? So in this case, every item, if an item is at index n, it has a reference to the item with index n+1. If that item exists, if the item is the end of the list, that reference is null, okay? Now, I can also implement lists where every item in the list knows not only the item that's next, but the item that's previous. So what I need to do here is I need to basically take my item class, which before only had this next reference, and now I need to change it so it also has a previous reference. So now, what does this allow me to do, right? I'd also have to change the constructor, which I haven't done here properly, right? So what does this allow me to do? Well, first of all, it means that I can walk the list both forwards and backwards, which can be useful sometimes. You'll also notice that I can maintain a reference to the end of the list. And I can do this even with a singly linked list. So one, question is, can I achieve O? Remember, when we added to the front of our linked list, we had O constant time performance, which is great because all I do is I change the start reference. What about if I want to add to the end? Can I also achieve O1 performance there too? And the answer is yes. All I do is I have my linked list class maintain an end reference as well that refers to the last item in the list. And whenever I want to insert something at the end, I can do it that way. Okay, so doubly linked lists are useful, because again, they allow us to either start at the beginning or start at the end and walk the list in either direction. And sometimes if I'm looking for a particular index in the list, it might be faster to start at the end and walk backwards rather than starting at the front and walking forwards, particularly if I know that the item is at the end of the list. So, for example, so far our lists haven't been storing how big they are, but you could, right? So for example, that size method that we implemented for a linked list, it actually walked the list all the way to the end. But that's kind of silly because when you add an item to the list, you could update a size variable that you store internally as a private instance variable, and then the size method could just return that rather than having to recalculate it every time. The idea is you control the list, so you know when items get added or removed. Therefore, you should be able to maintain a count internally and not have to walk the list to the end every single time. So one of the trade-offs, there's a couple of different trade-offs, and we're going to get to this full kind of summary of all the different trade-offs between these two different types of lists. So at this point, going back kind of a week, you guys have implemented lists where the items in the list were stored in an array internally, and you wrote code to work around Java's limitations with respect to arrays in terms of them being fixed size and things like that. So you did that. That was the first way that we implemented a list. And then we implemented the same list interface, but now we've done it using this concept of linkage, where each item has a reference to the next item, and that's how we establish order. We don't establish order by using an array, we establish order by using references. So every item knows the next item in the list. These two different approaches have trade-offs. Neither one of them is the right solution to every problem, and that's why the Java standard library actually includes both. There's a built-in array list that you can use, that you're used on MP3, and there's also a built-in linked list that operates pretty similarly to what we've been discussing. But there's another trade-off here. So there are different operations that perform differently on these two lists. But there's another trade-off, which is a time versus space trade-off. Okay, so let's look at this. So linked lists are faster for certain operations, but they consume more space to store the same amount of information. So let's look and see why that is. So with an array list, I had this array, and if I implement the array list the way that we had you guys do it, where every time I add or remove, I change the size of the array, that means that if I want to store n items, I have an array that stores n object references, where each one of them refers to one of the items in my list. So the size of that is kind of n, where n is the number of elements in the array. I have to store n object references. Let's look at our linked list, right? So our array list just had this internal array. Our linked list has one item for each item, so for each thing in the list. Everything I put into the list gets wrapped inside this item object. The item object has an object reference, so that's the same as the array list, but it also has an item reference for the next item in the list, and if I do a doubly linked list, it has a previous item reference as well, okay? So for every item that I put into my linked list, I not only have to store the object reference, which the array list also had to store, but I need to store two additional references, potentially two, one in your implementation, but at least one, right? So the object reference itself, and then a reference to this next item. So what this means is that if I want to store like n integers, an array list requires that I store n values, but the linked list for doubly linked lists requires 3 times n because I need to store the value itself, the value reference, a next reference, and a previous reference. So overall, the linked list is going to take up more memory. It's going to consume more of your computer memory than the array list for storing the same number of items, okay? So let's just keep that trade-off as well in mind when we look at the different performance trade-offs. All right, so let's go through and we're going to fill out this diagram. You guys will see questions about this on later quizzes, I guarantee it, right? But, and again, this is our first example of really thinking about doing algorithm analysis. And we've tried to make it very concrete. So if you get confused about why things perform the way they do, go back and look at the code that you wrote to solve the different array list homework problems and the different linked list homework problems. And we'll go over some of that code in class. And you can see exactly what's going on, right? You see that loop in insert and remove, or add and remove in your array list. You see the loop in finding the spot to insert, remove, get, and set in the linked list, right? So this is very concrete, right? You can see, in your implementation, the various code features that lead to different, these operations being in different performance categories. All right, so, and here, when we look at performance, we're going to distinguish between inserting at the front and inserting anywhere in the list, because inserting at the front turns out to be a case that the linked list handles very well, okay? So an array list, adding anywhere in the list, this is inserting an element, increasing the size of the list by 1 is on, because I have to copy all of the values from my old array to my new array. With the linked list, when I add to the front, it's O1. All I do is I change the start reference and then I set the next reference on the new item to refer to the rest of the list. That's it. Now you might wonder, why do we worry about this special case? Well, it turns out that there are some algorithms that use a list, but they only ever modify at the front. So they either insert things at the front or remove things at the front. Right? This is sometimes known as a stack. Think of like a stack of papers on your desk, right? Maybe you are too scared to insert anything in the middle because this is a huge stack. So you only add things to the top or remove them from the top. So you're only accessing that one point in the list. You can model a stack of papers as a list. And if you only remove things from the top and add things to the top, this is a sort of a special case of a list that's sometimes referred to as a stack. And a linked list will support that very well, because those insertions and removals at the top are O1. All right, so let's think about get and set. Here the array list does really well, right? So get and set are O1, because all they do is index into that internal array that the array list is maintaining. A linked list, on the other hand, for the general case of get and set, anywhere in the list is going to be ON. Because every time you get a value, it has to walk the list all the way to get to that spot. If it's the first item, it's O1. If it's the last item, it's ON. Average case, if you assume that my gets and sets are randomly distributed throughout the list, is ON over 2, and we round that to ON. All right, so insert anywhere. Now again, inserting anywhere in an array list is the same thing as adding to the front. They're the same operation. I have to copy the whole array. Linked lists, once I am doing insertions into the middle of the list, then things aren't as rosy as they were when I was only modifying the front. Now I actually have to walk the list to get to the right spot and then insert the item. And so that it's the getting to the right part of the list, it's that get item that you guys wrote as a helper function for your linked lists that becomes a problem. When I need to access an arbitrary element of a linked list, I'm always looking at ON, whether that's get, set, add, or remove. The linked list makes it very fast to modify the front, and if I do a little bit extra work, also the back of the list. And again, there are certain algorithms where if they only modify the front or they only modify the back, and that's the only place they care about, they may perform much better using a linked list rather than a array list. All right, so I'm going to leave this up. I'll come back to this slide kind of at the end when I finish up. But I'm happy to take questions about lists. We can also handle these on the forum and stuff like that. So this is our first data structure that we've looked at. It's a good place to warm up because lists are so similar to arrays. And those of you that have some prior programming experience in Python or whatever have already worked with lists. So now you're seeing a little bit, though, of the internals. Again, if you looked at, there's actual Java code that implements the array list class in Java or the linked list class in Java. You could go and find that code and read it, and you would probably recognize a little bit of what you would see there based on the conversations that we've had so far about how to do this, right? Now, again, those implementations are going to be much more sophisticated. They're going to play some games to improve performance. Some of those games we've talked about, other games you would find out by reading through the code. But you should have a starting point for thinking about how to work with this, right? Linked lists, linked lists get used all over the place, like I said before, right? Maybe we made them feel like there's something a little weird, like most of the time I would use an array list, and that's true in Java, but linked lists get used in a lot of places. Okay, so let's go bravely forward. So the next data structure, and the one that's going to consume us for the next few weeks until we get to talking about sorting algorithms, is something that's called a tree. And again, trees are going to be with you for many, many semesters, right? We'll talk about them now. You'll talk about them in 173. You'll use them in 225. You'll implement some different variants of them in 225. I think you'll also talk about them in 374. This is a very big and interesting and diverse category of data structures that essentially mimic a hierarchical tree structure, okay? Where there's a root value, and then each node in the tree has a parent, okay? And let's look at how these are actually represented. Okay, so the first thing we're going to do is we're going to introduce some terminology here. And this is terminology that we'll use when we talk about trees, and that you'll use later on when you get to other classes as well. Okay, so in a tree, we look at a set of nodes that are linked together. Unlike a linked list, they're not, each node can be linked to multiple other nodes, right? And this ends up producing something that looks like a tree. It's like kind of an inverted tree. It's like the roots of a tree. You have to kind of like look at it upside down if you actually want it to look like a real tree. In computer science, our trees grow downward for some reason. When we think about the linkage between nodes, right, we say that in this particular small tree, each parent, we can refer to a node in the tree as a parent if it has children. So this node that I'm calling the parent that's outlined in blue has, in this case, 3 children. Now, each node in my tree can have 0 or more children, but each child can only have one parent. So there's no way for a child to have more than one parent. Once I put a node into a position in a tree with a parent, it can't end up having another parent. It can have children, more than one children or 0 children, but it can only have one parent. So here's an example of a taller tree. We refer to the node at the top as the root. And again, this is a little weird because the tree is backwards, but whatever, you think of it as growing down. So the node at the top is the root. The root is the only node in the tree that does not have a parent. So see here, this root has one child, which is this node, but the root does not have a parent. There's no node above it in the tree. This node has 2 children, these 2 nodes, and then this node down here has 1 child. So the top of the tree is the root, and every tree that has a finite number of elements will also have at least one node that's called a leaf. A leaf is a node that has no children, right? So here, this node is the root, it does not have a parent. This node has a parent, which is the root node, and has 2 children. This node has a parent, and it has 1 child. This node and this node, the 2 that are marked blue, are leaf nodes. They have a parent, they're not the root, there's only one root in the tree, but they do not have any children. And again, every tree has at least one leaf node. A single node can also be thought of as a tree. That node is both a root and a leaf. But in a tree with more than one node, you're going to have at least one leaf. You don't have to have more than one, sometimes you just have one leaf, but you have at least one leaf. The tree has to stop somewhere. When we talk about trees, we can measure them in different ways. We can talk about the number of nodes that are in the tree, but frequently when we talk about algorithms that run on trees, one of the things that we're interested in is the depth of the tree. So the depth of the tree is the farthest you can get away from the root node. And we can number and define levels of the tree depending on how far away from the root are we. And what does it mean to be far away from the root? So the question is, how many nodes do I pass through on my way to a particular node in the tree? So the root is always at level 0, right? The root is 0 nodes away from itself. Now, in order to get to this node, I had to follow one link or one reference. And so this node is at depth 1 or at level 1. This node is at level 1. Now to get to this node, I have to follow another reference. This node is at level 2. And to get to this node, I have to follow a third reference. So this node is at level 3. Okay? And so the depth or the height of a tree is the maximum number of nodes or the maximum distance from the root to any leaf. Okay? And you'll notice different leaves can be at different depths in the tree. So this leaf is at depth 1. It's only 1 hop away from the root. This node is at depth 3. It's 3 references away from the root, right? I had to come to this node first, that was 1, this node second, that was 2, and now I got here. The leaf with the greatest depth defines the depth or the height of a tree. So, now given that we have a little bit of information about kind of what a tree is, what do we do with them, right? What kind of data can we represent using a tree, right? Because, when I talked about data structures, I should have pointed out something else, which is in computer science, we not only use data structures because they allow us to represent algorithms, we also use data structures when they do a good job of modeling real-world data or real-world systems, right? There are some data structures that we use because they exist in the real world. Like, there's data out there that has this form already, and in order to be able to work with it, we need to mimic that structure. And so trees are both, actually. Trees are used partly to implement algorithms on, but they're also used because, in some cases, they mimic real-world data, okay? So let's give you some examples. So the Java class hierarchy, maybe this feels a little bit too, like navel-gazing or something, but, we know that in Java, all the classes in Java are organized into a tree. The root node, the only class in Java that has no parent, is capital O object. Every other object or every other class, in Java fits somewhere else into that tree. If I don't declare a parent, or I don't declare that I extend another class, my parent is object. But there's only one node, there's one root node in the Java object tree. And Java uses that tree all the time. When you compile your Java code, that tree gets used to figure out, what methods you inherit from your ancestors and things like that. So this tree is not only, conceptual in the sense that we think about organizing classes into this tree, but it's also used by the Java compiler and by the Java runtime to do things like figure out what method to call and determine if you've overridden something from your ancestor, whatever. This tree gets used all the time. So the files on your computer. So I realize that I'm speaking to you in the year 2020, and some of you aren't even aware of the fact that there is a thing called a file on your computer. But it turns out that there are files on your computer. Those files contain data in them that is used by the programs that run on your computer. And the way that your computer organizes those files is into a hierarchical tree, where this is an organizational strategy that allows you to keep things somewhat organized, right? So you can put things into folders, you can make subfolders of those folders. It turns out that the position of every file on your computer essentially has a hierarchical structure. Those file names form a tree. Internet domain names, so we're going to talk more about the internet in a couple of weeks, but domain names on the internet follow a hierarchical pattern, and this is because control over those domain names also follows a hierarchical pattern. So if you want to create a new .edu domain name, like let's say you create another University of Illinois and you want Uni Illinois or something like that .edu, there's an organization that manages the edu suffixes in domain names. Everything that ends with edu, there's a group that runs that space, and you would have to go to them and say, I would like that domain name, and they would have to determine that you're actually an accredited or some type of educational institution, right, before they would give you that, right? So in the case of domain names, the tree represents something about how the domain name control is granted. We'll talk more about that in a second. But any data in the world that has a hierarchical structure, so you think taxonomies, right? All the different living creatures on Earth, zoologists have organized into a tree, right? And so, again, these are cases where trees not only are good for running algorithms, but also we need a tree in order to represent real-world data that's out there, right? So in order to have the compiler work with the Java object hierarchy, it needs a tree, right? Because that's how the Java objects are organized, right? So again, just to reiterate on a couple of these, here's the Java class hierarchy. Here's the tree of classes that's created by this particular set of extensions, right? So old dog extends dog. That when you say extends, what you're really doing in the tree is you're identifying your parent. So extends dog means that my parent class is dog. So I create this linkage. Both dog and cat extend pet. So that establishes these links. And then pet, remember, if I don't extend anything, then I automatically inherit from capital O object. Capital object becomes my parent. The capital object is the root. It's the only node that does not have a parent. Here's an example of your computer's file system. This over here is some shell commands that you can run if you're brave and interested in fooling around with this sort of thing. But it turns out that like on a Mac, and actually there's a lot more data here that I didn't show, but there are, your file system has a root. That's a directory that has no parent. And then inside that root directory, you can have, for example, other directories or folders with different names. Those folders can contain folders, and those folders that contain folders can contain folders. And this can go on, and eventually those folders can contain files. Okay? And what this means is that whenever you stick a file onto your computer, the name of that file is actually computed by looking all the way back to the root and using all the directories. And that's what allows you to have a file with the same name in two different places on your computer. So you can have the same file like test.txt in two different folders because your computer thinks about the name of the file as including all the directories that go all the way back to the root. And so even though the file has the same name to you when you open the folder, to your computer it has two different names. So again, domain name translation, and this has to do with not only how names on the internet are translated, which is something that we'll talk about in a few weeks, but also it has to do with control. Okay, so for example, if I want to get a new .edu or .com domain name, there's an organization that manages these that I have to go talk to. However, if I want to get a new .illinois.edu domain name, there's an organization on campus that I have to talk to. And then, for example, if I wanted to get a new .cs domain name, there's actually a group within our department that I have to talk to. So, just a couple weeks ago, when it was clear that we were going to need to do more things online, I went to them and said, hey, I'd like to get, cs125-help.cs.illinois.edu. I'd like to set up that name, and we'll talk about exactly what that means again in a few weeks. And they said, sure. But those were people that were just down the hall. I didn't have to go to some global consortium to get permission to do this because the way that domain names are managed also follows this tree hierarchy where as the domain name gets more specific, the people that you have to ask for permission become closer and closer to sort of you in the organization, right? So again, if I wanted to get cs125.illinois.edu, I would have to talk to somebody else on campus, but this would be more like of a campus-wide IT department. And they would probably say no, because they would say, well, that really belongs under CS. All right, so now let's talk about a specific type of tree. And this is the tree that we're going to be working with in this class. So again, there are many different types of trees. When you go on to 225 and other classes, you'll learn all about them. They're super cool. They all have different properties, and this whole space, there's a famous algorithms and data structures book, and the part about trees is like very long because there's so many different varieties of tree. But the type we're going to talk about in this class and the type you'll be programming with, something that's known as a binary tree. In a binary tree, we impose a new limitation, which is that each node can only have at most 2 children. It can have 1 child, it can have 0 children, but it can't have 3 children. Right? And if you looked at some of the examples we looked at, your computer's file system, that's not a binary tree. If you have a folder on your computer, you can stick 10, 15, 82 different subfolders inside that. That's fine. In a binary tree, we say each parent can only have up to 2 children. And this allows us to create this binary tree class where, for example, here's my tree class, and the one you guys are going to work with is a little bit different than this. But it has a right child and a left child, and then it stores a value as well. Because remember, when we structure data in a tree, we're usually not just using trees for their structure, we also want them to store data. It's a data structure. Okay? So with an array, the structure that I brought to the data was the order. the structure that I bring when I put things into a binary tree is quite different, and we can use it to do different things. But we'll talk about later some different algorithms that we can run on trees that turn out to perform much better than they would if I ran them on an array. Okay, so binary trees, 2 children, and to make our discussions easier, we'll talk about those 2 children as the right child and the left child. Again, not every node will have both a right child and a left child. Some nodes will only have a right child or only have a left child. Some nodes will not have either, in which case it's a leaf, right? All right, so here's a tree. This is a binary tree. And now what I'm going to start to do is I'm going to start to seed your mind with some interesting ideas related to the structure of this tree and a feature that trees have, which is called self-similarity. So let's just look at this tree for a few minutes together. I've got a root node that has the value 1. That root has a left child of 3 and a right child of 5. This node has a left child of 7 and a right child of 9. And let me point out something about this tree that's really interesting, and it turns out to be something that's really going to kind of undergird our discussion for the next week or so. And that thing is that every subtree of the tree, what do we mean by subtree? So if I start at the root and I look at only the portion of the tree that's hanging off the left side, right? So only the portion of the tree that is rooted at node 3, that itself is a tree. So if I imagine that I'm only looking at the blue colored nodes here, I'm still looking at a tree. This tree has root node 3. That has 1 child, which is node 4, and that has 2 children, a left child 6 and a right child 8. Now, I can continue this process. So let's say I look at the subtree that's rooted at node 4. That's also a tree. This tree has 3 nodes. It has a root node of 4, that node has a left child of 6 and a right child of 8. And I can continue this process. So the leaves are trees. A tree with 1 node is still a tree. That has, this tree has root node 8. It has no children. So it's both a root and a leaf. And I can continue this process on the other side of the tree. So the portion of the tree rooted at node 5 is itself a tree. Okay? The portion of the tree rooted at node 5 that's rooted at node 7 is itself a tree. And the portion of the tree rooted at node 7, that's the leaf node 10, is itself a tree. Right? So essentially, I can take this big tree and I can tear it into smaller and smaller pieces, and every one of those pieces is still a tree. And this turns out to have profound consequences for the kind of algorithms that we can implement on trees, because trees are one of the best places to learn a powerful programming technique called recursion. Recursion takes advantage of this self-similarity, because what recursion does is it requires us to do a couple of things, but one of those things is make the problem smaller in a way that preserves certain aspects of the problem, right? So the fact that I can take this big tree and I can decompose it into smaller and smaller trees means that this is a data structure on which I can write recursive algorithms. So recursion is a term that really means a variety of several different things. We're going to look at recursive implementations of algorithms. We're going to talk about recursive algorithms. But at a fundamental level, recursion, right? Think about it, recur, right? What does it mean to recur? In this case, it means when something is defined in a way that includes itself or other parts, other things of its type. So here's an example of recursion. I have a class called tree. The definition of my class includes references to other instances of a tree. So trees inherently are what we refer to as recursive data structure, right? The definition of our tree incorporates a class being defined in terms of itself, right? So part of the definition of a tree is a class where I have a right child and a left child, which themselves are instances of tree, right? Now again, recursion in computer science is usually, we think of it not only in terms of data structures, but as a problem-solving technique. And that problem-solving technique we apply when the solution to a problem depends on solutions to smaller instances of the same problem, okay? Now, recursion is a concept that can be difficult to wrap your mind around. And as everything else that we've taught you in this class, the best way to do this is to practice, and you will get lots of practice. We have a whole, cavalcade of recursive homework problems that we're going to start up in a couple of days. And you guys will get tired of writing recursive algorithms on trees, but you will get a lot of practice doing it. Recursion is one of those things that, people don't always get right away. I remember, actually, almost 20 years ago, learning recursion for the first time and feeling like, oh my gosh, this doesn't really make very much sense to me. What's going on here? It can be difficult to wrap your mind around it. You will get there. It takes practice, it takes time. Ask questions, but don't be alarmed if it doesn't come immediately to you, even if some of the other things in the class have, right? Even if you're new to programming, it's like, oh, this all made a lot of sense. You get to recursion, and sometimes it's like, oh my gosh, this is really weird. I don't really understand what's happening. Stay with it. Keep practicing. Keep thinking about how these things work, and it will start to seem more natural. At the end of the day, recursion is a new tool in our toolkit for solving problems. As a computer scientist, we want to use every possible strategy that we can to instruct a computer how to solve a problem. And recursion is just another strategy. So far, the algorithms that we pursued in this class are what's called iterative algorithms. They proceed fundamentally by repeating a sequence of steps until they arrive at an answer. So for example, when I'm taking the sum over an array of numbers, I start out with 0, then I go through the numbers one at a time. This is iteration. And I add each number to my sum until I run out of numbers to add, at which point I declare that the algorithm is done. It's computed the sum. Recursion gives us a new framework, a new approach, a new mental model for thinking about problems. Recursion and iteration are not competitive in the sense that they can both solve the exact same set of problems. There are no problems you can solve with recursion that you cannot solve iteratively. And there are no problems that you can solve iteratively that you cannot solve with recursion. Sometimes the solution that you arrive at to an algorithm that is iterative is great, and the recursive solution is awkward. And sometimes the recursive solution is elegant, and the iterative solution is awkward. But there are there's no problems that you can't solve using iteration, and there's no problems that you can't solve using recursion. People always have this misconception, but there are also fairly straightforward ways of taking an iterative algorithm and making it recursive, and taking a recursive algorithm and making it iterative. All right, so let's go through an example of this. And again, this is a topic that we are going to dwell on. We're going to spend lots of time here, so don't freak out if this isn't making sense right away. I hope it will in a couple more classes. Let's look at how we count the number of nodes in a tree. Okay, so let's say that we had this tree and we wanted to determine how many nodes were in it. So one way we could do is we could count this iteratively. And this is a place, trees, it turns out to be a place, a data structure, where iterative algorithms are actually very awkward to write. Can you do it? Yes. Is it elegant? No. Okay? But let's say, we could find some way to visit every node of the tree, and we would basically increment a counter every time we got to that node. And it's really the process of getting to every node in the tree that turns out to be very awkward. Okay, but let's imagine we could do that. So we start at node 5, that's the root, and then we visit node 3. So now we have 2 nodes, 3, 4, 5, 6. And then we're done. We say the tree has 6 nodes. So this is an iterative algorithm. And again, you can try to implement this. We're going to give you a tree counting homework problem coming up quite soon. Solve it recursively, and then if you're brave, give it a try iteratively. I doubt that, I actually think, given the constraints that we force you to operate under, you won't be able to do it iteratively, but I would certainly be happy to be proven wrong. All right, so now let's talk about how we would approach the problem recursively. And this is kind of where we'll end today and pick up on Friday. So in order to do something recursively, what we need to do is we need to make the problem small, right? And so here's what we're going to do. We're going to basically say, we're going to find a way to break the problem into smaller pieces. At some point, there will be a problem that is so easy to solve that we won't need to break it into smaller pieces. And in fact, there won't be a way to break it into smaller pieces anymore. And then what we need to do is combine the results of those smaller problems together. Okay, so let's start off by breaking the problem into smaller subproblems. Okay, so here's one way to think about that. So rather than counting the entire tree, I'm going to basically say, look, I don't know how to count this entire tree. I don't have an algorithm for that. Instead, but here's what I do know. I do know that the number of nodes in the tree rooted at node 5 is equal to the number of nodes in the tree rooted at node 3, those are the pink nodes, the number of nodes plus the number of nodes in the tree rooted at node 10, those are the orange nodes, plus 1, that's me, right? So look, basically my algorithm says, I don't know what the number of nodes in the tree rooted at node 5 is, but I do know that it's equal to 1, I'm counting the node 5, plus the number of nodes in my left subtree, that's the tree rooted at node 3, plus the number of nodes in my right subtree. So you might think, have we really made any progress here? Because I started with one problem, and now I have 2 other problems. So now I have to figure out, how do I count the number of nodes in the tree rooted at node 3 and count the number of nodes in the tree rooted at node 10? But let's just continue on, right? Because I want to point out, those 2 problems are smaller than the problem I started with. I started trying to count a big tree, and no matter how many nodes are in the tree, there are fewer nodes in my left subtree and fewer nodes in my right subtree than there are in the entire tree. All right? Okay, so now I start the algorithm over again, but I run it on the tree that's rooted at node 3. And this tree basically tells me the same thing. It says, look, I don't know how many nodes are in this tree, but here's what I do know. I know that the number of nodes in this tree is equal to 1, that's me, node 3, plus the number of nodes in my left subtree. And in this case, I don't have a right subtree, right? So I don't know how many nodes are down there, right? But I do know if you could count the number of nodes that were rooted in my left subtree at node 7 and add 1 for me, you would know how many nodes are in the tree rooted in node 3. Okay, so again, let's keep going. So now we get down to a problem that's simple, right? Remember, one of our tenets here was make the problem smaller until we find a problem that's so small, we kind of have to solve it. So now we're at node 7. Node 7 has no children. So what is the number of nodes in the tree rooted at node 7? It's 1. We're done. This is a leaf node. So all we need to be able to say is it's got no children. So this node defines a tree. The number of nodes in the tree rooted at node 7 is 1. Okay, so I finally solved a problem, and I'm excited. But it's actually better than that, because I actually solved a few problems. But let's keep going. So let's look at the other side. So let's look at node 10, right? Because remember, I still have to count this part of the tree. I proceed the same way. Node 10 says, hey, I don't know how many nodes are down there, but I do know if you could count the number of nodes that was rooted at my left child, node 9, and the number of nodes that was in the tree rooted at my right child, which is node 1, and add 1 for me, that would be the number of nodes in the tree rooted at node 10. And so I do that, right? I go down to node 9, and again, I've reached a leaf node, so I know how many nodes are in the tree rooted at node 9. It's 1. Okay, so I'm done. I get to node 1. Node 1's also a leaf node, so I know the number of nodes that are in the tree rooted in node 1. That is also 1. Okay? So at this point, I know the number of nodes in the tree rooted at node 7, and the number of nodes in the tree rooted at node 9, and the number of nodes in the tree rooted at node 1. And now what I need to do is start using that information to solve these bigger problems that I delayed solving as I was working my way down the tree, right? So remember, node 3 said, hey, if you could count the number of nodes in my left subtree, we would know how many nodes are rooted in the tree at node are in the tree rooted in node 3. And I'm like, hey, I counted the number of nodes in your left subtree. And 3's like, awesome, okay, well add me. And now we know, right? 10 said the same thing. 10 said, hey, if you could count the number of nodes in my left subtree and my right subtree, and add 1 for me, you would know how many nodes are in the tree rooted at me, node 10. And I'm like, hey, I counted the number of nodes in your left subtree and the number of nodes in the right subtree. And I know that it's 1 in both, and now I'm going to add you, and so the number of nodes in the tree rooted at node 10 is 3. And now I'm done, because I go to node 5. Node 5 was like, I sent you off on a wild journey. I said, hey, in order to count the number of nodes in the entire tree, you've got to count my left subtree, rooted at node 3, and my right subtree, rooted at node 10. And you're coming back and you're saying, hey, I did those things. I know that in your right subtree, there are 3 nodes. And in your left subtree, there are 2 nodes. And so I'm adding you, and I know that this tree has 6 nodes. So that's the journey that we go on when we solve a problem recursively. We start, in this case, we started at the top. And I'll just go through this diagram again, right? We started at node 5, and we said, okay, well, I'm going to break the problem down and make it smaller. So I need to count the nodes in the tree rooted at node 3 and the nodes in the tree rooted at node 10. And I started working on those problems. And then eventually I got to the point where I was solving these very simple problems because I got to leaf nodes. Once I got to a leaf node, I didn't have to do any more work, okay? Because I knew the number of nodes in that tree. And I could run the same thing over on both parts of the tree. And then I started to assemble the information back together to the point where I could go all the way back. So first I would go back to node 3 and say, hey, I counted your left subtree. And go back to node 10 and say, hey, I counted your left and your right subtree. And then I go back to node 5 and I'm like, I have counted your left subtree, I have counted your right subtree, and I am ready to solve the puzzle. And that's what we did. All right, so I think we're basically out of time here. I will pick up here on Friday. We will go through this piece of code together, and we will implement our counting algorithm, and I will show you precisely how elegant and beautiful a recursive algorithm can be. Okay, so as a reminder, it's Wednesday, so we're not running office hours today. We will have office hours again for MP4 tomorrow starting at noon. I congratulate everybody on the midterm. It seems like people did fairly well. Proud of you guys for that. I hope everybody is staying safe, taking care of each other. We are still doing our best to run this class as well as we can in this new format. I'm continuing to work with the staff to find new opportunities to do things better. Feedback from you guys is definitely welcome. And again, keep in mind, I love this stuff. I think it's really important. I hope you guys are able, given your circumstances, to continue your education. But there are some other things in life right now that you might want to think about giving a little bit more priority to. And if that means that you do a little bit less on CS 125, I think that's totally okay. So, take care of the things that you need to do and the people around you that might need your help or support. And I will be back with you live streamed at 10 a.m. on Friday. See you then.